All right. So then let us take a look at what we're looking forward to. Visualizer. Basically, a lot of math. We love math in this class. So let's take a look. We know currently, actually, let me switch to just me. We know currently, so if you go to your view for speaker view. Yep, cool. We know currently that here we have a balloon. There is pressure in this room. It's in the, it's from the atmosphere. This room has a temperature. This balloon right here doesn't have anything other than, atmospheric pressure inside and out. And it is open, so particles can flow in and flow out of it. So I'm going to put some particles into this balloon. So currently, give me 1 second. Currently, we have particles in this balloon. Now, if I put more particles in this balloon, the volume of the balloon will increase. So we can assume then that volume, pressure, and temperature are connected by the number of particles. So if I tie this off, that is a set number of particles. If I release the particles here, the volume goes down. Right? So let's go ahead and I'm going to tie this off. Boom. Now it's set. So let's go back to our notes page with PV equals nRT on page 6. Let me show you what that looks like. Now we deal with a world where gases in our mind are hard to understand and deal with. In reality, scientists from yesterday, they actually enjoyed dealing with gases because they were easier for them to look at, measure, because they would contain them by using water and glass and stuff like that. For us, we sit there and think, oh, it's easier to sit there and take something solid and use it. For them, they didn't know all of the combinations of ratios and stuff that we know today. So they were able to find this stuff out by using gases. All right. So at this point, scientists began figuring out more and more about gases to experiment. If we imagine standard temperature pressure and we measure out 1 mole of gas, what would be the volume at STP? So if we take a look, 1 mole of gas, we know, is 6.02 times 10 to the 23rd particles. So that's equal to 1 mole. Volume, that's what we want to find. Pressure, well, STP, standard pressure, is 1 atmosphere. Temperature at STP is 0 degrees Celsius, which is 273 Kelvin. That was a big mistake that I found on a lot of homework was people did not change from Celsius to Kelvin. That's a downer. Does anybody remember every 1 mole of gas at STP? How much space that takes up? It takes up 22.4 liters of space. 1 mole of any gas at STP, it doesn't matter what gas it is, it takes up 22.4 liters of space. This is called the molar volume of gas at STP. We actually talked about that right here. 22.4, right? So just keep that in mind. That's a number you want to get in your head, just like 6.02 times 10 to the 23rd. So we know that pressure and volume and temperature are all connected. Pressure and volume, if one goes up, the other goes down. Temperature, if it goes up, pressure and volume go up. Temperature, if it goes down, pressure and volume go down. So these temperature and volume are directly proportional. So let's think about number of particles then. If I put more particles in here, what happens to volume? Home viewers. If I put more particles in here, what happens to volume? Increases was mentioned at from the people at school. That is correct. It increases. Well, if I were to take instead of a balloon, something that can stretch a lot, if I were to take a tire or a canister like this, right? If I put more particles in there, what happens to pressure? The can can't get bigger or smaller. More particles in there, the pressure inside gets what? It increases, right? So if we put more particles in here, the pressure would increase. If we put more particles in here, the volume would increase. So pressure and particle number, they're directly proportional, and volume and particle number are directly proportional. As particle number goes up, pressure and volume go up. So we are going to put the number of particles down here with temperature because it has the same effect on pressure and volume that temperature does. If temperature goes up, pressure goes up. If temperature goes up, volume goes up. So it's on the bottom here. And we are going to set that equal to R, which is called Riley's constant, but we don't know that yet. So our pressure, STP, 1 atmosphere. Our volume, we said 1 mole of any gas at STP takes up 22.4 liters of space. Our temperature, well, at STP, that's 273 Kelvin. And our number of particles, well, we said that that is 1 mole. Do any of our units cancel out here? Are any units on top the same as the ones on bottom? Atmosphere Kelvin, liter mole. Nothing's the same. 1 times 22.4 divided by 273 times 1.
It's about 0.08205.
0.08205. Again, I said that none of my units cancel out. So this constant, Riley's constant, will be atmosphere liter per Kelvin mole. Now, a lot of times, this is changed to instead of 0.08205 to 0.0821. Now, instead of atmosphere, what if we had millimeters of mercury? Well, instead of 1 atmosphere, we would have 760 millimeters of mercury, 22.4 liters over 273 Kelvin mole. 760 times 22.4 divided by 273.
The answer is about 62.3589.
Again, this would be millimeters of mercury liter per Kelvin mole. And that, if you were given instead the pressure in millimeters of mercury, you could use this. If you were given the pressure in atmospheres, you could use this. If you were given the pressure in milliliters, you would need to change from milliliters to liters. Otherwise, if you use this, it will not work correctly. You've got to make sure you have the correct units for your R constant that you do given into your problem. The new formula was rearranged to be PV equals the number of moles times R constant times temperature. All of these right here are R constants. We are mainly using millimeters of mercury in atmospheres. Remember, 1 atmosphere is equal to 760 millimeters of mercury. So that brings us to page 11. I need to get a review sheet for this gas salt stuff for you guys. So it says how many moles of oxygen is present in 256 liters at a 1.05 atmosphere and 18 degrees Celsius? First thing, change that to Celsius to Kelvin. 18 plus 273.
The answer is 291.
291 Kelvin. We have liters, so that is a volume, and we have atmospheres, so that is a pressure. We now have the temperature. We know that PV equals nRT. That's our new equation for this part of the unit. We want the number of moles, so we're going to solve for N. In order to isolate N on this side of the reaction, we need to divide both sides by RT. Now it is plug and chug, or whatever your algebra math teacher calls it, 1.05 atmospheres times 256 liters divided by R. Well, I'm in atmospheres, so I want to choose 0.0821 liter atmosphere per mole Kelvin. And temperature is 291 Kelvin. Notice kelvins will cancel out, atmospheres will cancel out, and liters will cancel out. That leaves me 1 over 1 over mole, and the inverse of the inverse is the normal. So this will give me moles. If it's on top, I multiply. If it's on bottom, I divide. 1.05 times 256 divided by 0.0821 divided by 291.
It's about 11.251.
3 significant digits for all of these involved. So 11.3 moles of O2. Questions there? Let's try another one. How many liters of gas? So they give me the number of moles, they give me the pressure, and they give me the temperature. If PV equals nRT, I want liters. I need to isolate V. So I need to divide both sides by P. 0.521 moles. I'm in millimeters of mercury. So that's going to be 62.4 liters times millimeters of mercury divided by Kelvin moles times the temperature, 491 Kelvin. We're going to divide this whole thing by 277 millimeters of mercury. Note, Kelvin cancels out, moles cancel out, and millimeters of mercury cancel out, leaving me with liters. That's what I want. It's a volume I want. 0.521 times 62.4 times 491 divided by 277.
The answer is about 57.6267.
3 significant digits all around, 57.6 liters of gas. That's PV equals nRT, folks. For tomorrow, I'd like for you to do 3, 4, 5, and 6. Basically rearranging this equation to solve for one of the variables involved. If you have questions, by all means, stick around after the Zoom. I will be here to answer them. If you don't, get out of here and get 4 problems done. You got, you got 20 minutes to do it. Have a great day. Take care. Be safe. Pet your kitties. Bye.
Is tomorrow a black day? I mean, is today a black day?
Today is a red day. Tomorrow is a black day.
Okay.
Yep. Am I going to see you tomorrow?
Depends on how today goes. So I don't know.
All right. Take care of yourself.
You too.
Thank you.